Hello, welcome to CSC 7132, Operating Systems and Networking. My name is Brady Chen. I'm going to be your instructor for the class for this semester. So the operating systems basically deals with the computer software that manages the computer hardware and the software resources and the other programs. So it is a software, it's a computer software, but it's not a specific software that deals with a specific task, like a computer game, or like an office software, like a Microsoft Word, Excel spreadsheet that dedicated to a specific task. But it is a general software that is used to manage the computer system. Okay, let's first start with Module 1, the Introduction to the Operating System. Section 1.1, the role of an operating system. Now, the first question is, what is an operating system? Now, I copy the definition from Wikipedia. It says, an operating system is system software that manages the computer hardware, software resources, and provide common services for the computer program. So it is a system software. So it's a software. Okay. And it's a general software that manages the computer system. So here are some of the examples of operating system. So the most popular one used at the home computer is the Microsoft Windows. That's one operating system. Now, most people use Apple, like if you use the iPad, that's iOS, and also you can use the Macintosh. That's also the Apple operating system, Mac. Okay. Now, most of the smartphone use Google Android operating system. Okay, that's also operating system. Now, Apple iOS, we mentioned that earlier. And there's another operating system which is widely used in the computer server. That's a Linux operating system. Now, Linux operating system is an open source operating system, which is quite different from Microsoft Windows. We'll talk about this later. So what's the difference between Microsoft Windows, which is proprietary software operating system, and a Linux operating system, which is an open source operating system? Section 1.1, the role of an operating system. A basic question you may ask is, why we need to learn an operating system? Why we need an operating system? Okay, so to answer that question, let's take a look at the diagrams on the right. So if you look at the top one, so if you're a computer hobbyist, you probably can easily tell what is this, right? It's a desktop computer case which contains the computer hardware. So there's a CPU in there, there's a memory and a hard drive and some other peripherals. Okay, so for the CPU, you actually don't see the CPU. Now that's a cooling fan. The CPU is actually behind the cooling fan, because the CPU is going to generate a lot of heat, so you need a cooling fan to cool the air temperature down. So now the memory normally inserted in the memory slot. Some computer have 2 slots, and some computer have 4 slots or even more. Okay, so that's the computer hardware. Now look at the bottom view. That's a Windows Explorer in Microsoft Windows operating system. So now this is actually user's view, okay, of the computer system. Now this is actually the hardware. The hardware is kind of ugly, but the user's views mostly looks well organized. Okay. Now, most people who use the computer system, they operate in the user's view. So they may open the Microsoft Windows Explorer, they create a folder, they create a new file, they edit the file, and they save the file. Okay, so they can create a different type of files like a Microsoft Word, Excel spreadsheet, and a PowerPoint presentation. So people want to operate on the screen. Okay. So for most people, they don't even care what's happening in the computer hardware. What's happening? Okay. So now that's the gap between the user's view of a computer system and the actual computer hardware. Okay. Because most users don't want to deal with this hardware, because if something goes wrong, they have no idea what's going on. So now the role of an operating system is to bridge the hardware and the user gap. Okay. So user actually perform the operations on the screen, and then the operating system going to translate that user operation into the actual action under the hardware level. Okay, normally hardware level is called the lower level operations, and the user's operation is called high level operation. So now that gap, that mismatch between the low level capabilities of hardware and the high level needs of the user must be bridged by system software that include the compilers, interpreters, editors, linkers, and the operating system. Okay, so hopefully most users don't need to deal with that one. So these compilers, interpreters, editors only actually operated by the computer professionals. They're going to translate the user's operation into the actual operation at the hardware level. Okay, so operating system is the software that runs on bare hardware of a computer. So it's actually a software running on the hardware that provides essential support for users. So then the user can focus on their high level operation. So they can, create the game, they can create Offices, Microsoft Word, and they can create the Excel spreadsheet, they can create the music, the MP3 music, and or MP4 videos. So they can create all these applications at the high level. And then let the computer operating system translate your operation into the low level operation. Now, from user perspective, an operating system is viewed as an extended machine. They actually do this through two techniques. One is the abstraction. The other one is virtualization. Now, what is abstraction? Take a look at the example. So if I want to perform a job, I'm a user for the computer system. So I want to perform the copy job. So I want to copy a document, copy a file, my Microsoft Word file or Excel spreadsheet. I copy this file from one folder to another one. Now this sounds like one single operation, right? Now remember that the two views for the operating system, for the computer system. One is the user view. The user actually view the computer system as a screen that which contains the graphics object, like a Microsoft Windows and Linux. So you can see the Windows Explorer and a folder and a whole bunch of files. Okay, that's the user's view. Now, the user want to perform a copy operation. Okay, now this copy operation has to be done at the lower level, the hardware level, right? So this is actually the kind of job for the operating system. Now, for each single copy command, it consists of a whole bunch of operations at the lower level, the hardware level. Okay, so that's the abstraction. So user perform one single operation. Okay, so user say, okay, please copy this file, and then the computer system actually perform a couple of operation at the lower level, at the hardware level. Now, so abstraction is the act of removing the important details and the attributes of the objects. Okay, so in this case, the detailed operations of hardware level are hidden. User don't care about this level. All user cares about is the operation at the high level, which is copy a file from one folder to the other. That's abstraction. So you hide the details, the ugly part of the operations, and just show user the beautified part. Now the other technique is the virtualization. So virtualization is the act of creating the illusion of having one or more objects with more described characteristics of that than the real object. Okay, so this actually happens when a computer system is very powerful, and typically, so you can only use small portion of the CPU to perform your operation. For example, if you want to copy a file, and then your CPU is so powerful, so it will perform your job very quickly. Okay, and then in that case, the virtualization allow us to partition the CPU power into a couple of fractions. Each fraction performs certain operations. And then now from user perspective, each fraction looks like an independent machine. Okay, so this is actually very interesting. We will talk about this in much details next slide. So the virtualization is basically create some kind of illusion that you actually are working with multiple objects. Now, but actually at the bottom level, at the lower level, it's just one piece of hardware, but it creates an illusion of many different machines, many different operating systems. Okay, that's the virtualization. Okay, let's take a look at the example. Now this is an example from the Zai book. So if you read the zybook. It is actually in the zybook section 1.1. It's a participation activity 1.1.2. Now, the zybook give you some kind of ammunition so you can understand this concept, more clearly. So let's assume, so we want to copy a file from a hard disk into a memory location, M. So let's look at the lower level. What does this operation consist of? Okay, so you first need to copy block location on disk. Copy block location on a computer block location on disk. So you need to calculate where's the block location of this file. And then you move read and write arm into the position. And both of this operation happens on hard disk, hard drive. So if you look at the picture on the right side, so this is a typical hard disk which consists of a magnetical disk. All the data are stored on the surface of this magnetical disk. The data stored on a magnetical surface of disk, and each disk consists of a whole bunch of circle. It's called a track. And then also from the center of the disk to the edge of disk, you're going to create a shape. It's called a sector. Now, so you can locate a disk location by specify the sector number and the track number. For example, if this is a track 100, then you're going to say track 100 and the sector. So suppose this is sector 0, 1, and this is 2, so sector 2. Okay, I'm just give you an example. So then it's a track 100, sector number 2. Okay, now this is a block. So computer block location on disk. Suppose the file is actually stored in a couple of blocks, not just one. So here, okay, here, and here. So it's stored on block, this one, this block, this block, this block. The first block is track number 100, the sector 0, track 100, sector 1, track 100, sector 2, track 100, sector 3. Okay, let's say 4 blocks. Okay, so then you check for position errors. That's part of the job for operating system. And then you transfer the data to memory, start at the M. So these data are going to be transferred to the memory. Now, before you do this, so you need to compute the block location on disk and move the read and arm into position. So basically, that's the read and write arm. So that's the header. Okay. So you actually move, this arm back and forth, and rotate the magnetic disk so the header can reach the block, and then the header start to read the data on the block. So this is what happens. So that's the reason why when you read the data from disk, you're probably going to hear the noise. So the disk, the magnetic disk going to rotate, and the header going to actually, the arm going to move back and forth. So you're going to hear the clicking sound. Okay, so now, so the header start to read the data in a block. Okay, and then check the position error and transfer the data from the hard disk to the memory. Okay, so here's the memory. So you have a memory location 0, 1, 2, 3, M. That's memory location. So you copy this piece of data, okay, to here. That's a low-level view of copying a file, a whole bunch of blocks from your hard disk into the memory. Now, this is too much, right? So the user don't want to know the details of this. So they, using the abstraction, you can actually, at the high level, you basically summarize this operation into one operation. That operation is called read block n into memory at the location m. So that's one operation. However, that operation is still too complicated to most of the people, because when I actually perform a computer operation, what I do is I want to copy a file from one location to the memory, from one location to other places. I want to copy a file, right? Now, what does block n means? I don't know, because I still need to know how this hard disk works. So that's still not good enough. So from user perspective, this is what I want. I just want the computer to perform the copy of a file F1 to file F2, not this, okay? So then there's another level of abstraction. So in this level, so you find out, okay, if I want to copy a file F1 to F2, now F1 may take a couple of blocks. Like I said, F1 may store in block here, block, couple of blocks, okay? So that means, so you need to actually perform a couple of operations to copy a complete file, okay? So first you need to create a file F2, that's the target file, and then open the file F1 from reading and repeat all blocks I of F1. So if F1 takes 4 blocks, then you're gonna actually do the loop for these 4 blocks: block 0, blocks 1, block 2, block 3. Okay, and then for each block, you're gonna perform read block I into memory buffer, and then eventually write the memory buffer to block J in the hard disk, or no, in the memory. So that's another level of abstraction. So from the user level, that's it. This is the one you want to operate. And then this is going to convert into these sequence of command, and these sequence of command are going to perform these operation multiple times, and then that's the bottom level. That's the abstraction. So the abstraction may actually happen multiple times at the multiple level. Now the virtualization is another thing. So in this particular example, so when you actually transfer the data from memory to from your hard disk to the memory, starting at the M. So now you can say, okay, I transfer data, copy the data from my hard disk block, certain block, to memory starting at the M, right? So now you assume that this M is the memory location, right? Most of the case, yes, it is. But there's a disadvantage if you actually directly use the physical memory location M for the command, because the command is not really flexible, not portable. So that's why, so that this transfer the data to the memory for that command, in many computer systems, they're going to actually perform these transfer to using the virtual memory. So the virtual memory is not real memory. So virtual memory say, okay, transfer to AM. So then the virtual memory is basically has the same structure as a physical memory, but it's not really physical memory, virtual memory. So the virtual memory is, maybe you can say, oh, transfer the data to the memory, start virtual memory started at the M is 0, so you transfer from 0, 1, 2, all the way to whatever, K, for example. Okay, now that's a virtual memory. Now, eventually, you're gonna actually store this piece of data into the physical memory. So then the virtual memory and the physical memory need another mapping. So you're going to map a virtual memory to the physical memory. Now, why you want to do this? Because if you actually perform the command directly to the physical memory, the memory location M may not be available. So then your command is going to fail. But if you actually say, oh, I create a virtual memory, say, transfer the data to the virtual memory, and then the operating system is going to find out some free memory space. Okay, so then I'm going to copy this data from virtual memory to the actual physical memory, because I know this piece of physical memory is free, so I copy to it. But so the virtual memory 0 may not copy to the physical memory location 0, right? Virtual memory location 0 may not copy to the physical memory location 0. It could be 0 copy to 100, and then the virtual memory location 1 probably going to copy to 101, and the virtual memory location 2 going to copy to 102. So you can actually copy to the actual physical memory location. So each time when you map the virtual memory and the physical memory, the mapping could be different. That will give you some kind of flexibility. So otherwise, you have to copy to this particular memory location, and then the operation fails, even though you have enough memory to deal with your job. Okay, that's the good thing about the virtualization. Now, in the previous slide, we just mentioned that from user point of view, an operating system can be viewed as an extended machine. Now, many times, the operating system can also be viewed as a resource manager. Now, why is that? So let's say we have a very powerful computer system. So we have a program, so we're going to run the program on the computer system. Now, a typical program, once it's created, alternates between three phases. Okay, import, computation, and output. So the computer is actually, a program is created. So then it requires the import value. You need to import so the program can run. So now that's called a computation. Now after a program finish the computation, it should generate an output. So these are the three phases for a program. So now the import and output is sometimes called I/O phases. Okay. Now this computation sometimes it's called computation phase or CPU phase. Okay. Now when a program is in the import phase, the program is not using the CPU. Okay. Also, if the program is the output phase, it's not using the CPU. Now, however, during the program is in the computation phase, then it is using the CPU to do the computation. That at this moment, the program is not using import and output. So it's just basically alternate between the I/O phases and the computation phases. Now, that's a kind of waste, right? Now, if you actually have a program, you actually running in the import phase, then the CPU is idle. Okay, and then when you do the computation, the I/O is idle. Okay, so that's the reason why it's not really a good idea to just run just one program. So modern computer systems typically support multiple programs running concurrently. Now sometimes we call these multi-programming environment. So now if you run multiple programs on a computer system, somehow you need to record which programs is using which resources. Okay. So then the computer can actually optimize the use of all computational resources to ensure a good overall performance. So because if multiple program running and they just conflict to each other, and the one program is using the CPU, and the other one also wants to use the CPU, and then it just causes some conflict. Now, somehow we should make sure this is not going to happen. Okay, so that's why one of the main tasks of an operating system is to optimize the use of these computational resources. And that's the reason why operating systems is also called a resource manager. Now, depending on the nature of the programs. Now, sometimes programs are characterized as CPU bound and I/O bound. Okay. Now, a program is called a CPU bound. That this program actually use much of the CPU resources, and they use small portion of the I/O resources. And then the I/O bound program is sometimes use most of the I/O resources and use less CPU resources. Now, one of the example for the CPU bound program is like some of the program that do the scientific computing. So typically, you're going to actually import the data, and the program going to run to calculate the result. So they're going to actually generate a lot of data, collect a lot of data, and do the computation and give the output. Now, during this time, the program going to use most of the CPU resources to do the computation. Now, I/O bound programs basically use the input-output most of the time. One of the example is like the program that a program that is running the social media application. So people basically, type a couple of lines of message and then hit the enter and send it out. And then most of the time, the CPU is idle because it's not going to use the CPU. The only the time when they use the CPU is when the user is type the message and send the message. Okay, so there's a kind of, now if you look at the a diagram, so that's a CPU usage. Okay, now CPU bound is most likely is kind of program that running like this, and the I/O bound is like so we both talk about CPU usage. Okay, utilization. Now I/O bound is most likely like a burst in natural. So it used the CPU for a very short period of time, and most of the time it's just idle, and then use the CPU again. Okay, so these are the two different type of programs. Now, because of the nature of these two different type of programs, it's always good to utilize these programs to optimize the usage of the computer resources. Now, multi-programming is a technique that keeps several programs active in the memory and switch executions among the different programs to maximize the use of computer CPU and other resources. Okay, so that's called a multi-programming. Now, why multi-program works? Because of this nature of these programs. Sometimes one program is use the CPU, the other program is not use the CPU, use the I/O. So you can actually take advantage of the availability of the resources to run multiple programs. Now there's another terminology, it's called time sharing. Okay, time sharing is actually a multi-programming. Okay, so it's an extension of a multi-programming where the CPU is switched periodically among all active computations. Okay, so multi-program basically means, one computer is using the CPU and then the other program is waiting, and once the computer actually complete the using of the CPU, then the other program pick up the CPU and start to use them. Now, time sharing actually, it is actually switching of the CPU usage, but it's switched periodically mostly by the computer hardware. Okay, so in the time sharing, all these programs are running in the computer system, and they take a turn to use the CPU resources. Okay. Now let's take a look at the example and illustrate how this multi-programming works. Now, this is actually the participation activity 1.1.7. If you want, and also in the Zai book, they have an animation to illustrate how this multi-programming working. But let's take a look at the example. I have two processes, process 1, process 2. Process 1 and process 2 share a single CPU, a computer system with one CPU, and two independent I/O devices. Okay. Now you have two processes, process 1, process 2, and you have three resources, CPU, an I/O device 1, and I/O device 2, right? Okay. Now each process execute a computer bound phase, or sometimes called a CPU phase, of 10 times 10 time units, followed by an I/O bound phase of 10 units. Okay, 10 time units. Now let's see what's the performance if I run these two programs on a computer system. Now we have three actually questions. One, without multi-programming. So that means only one program gonna run on the computer system. Now, the second case is that with multi-programming, and then the third case is using the time sharing. Okay. Let's take a look. Okay. Okay, let's provide answers for each of the cases. Now, remember, the probe process P1 and P2, each going to execute a computer bound phase of 10 computer bound phase of 10 time units. Okay. Now that time units could be a second or microsecond or whatever. And also, each gonna actually followed by 10 time units of I/O operations. So each just run a computer bound operation for 10 times units, and then followed by 10 time units of I/O operations. So let's take a look at the first case. So the first case says the operating system does not support the multi-programming. Okay, so that means at any particular time, only one program is running. So let's actually assume P1 start to run. Okay, P1 start to run first. Actually, it doesn't matter whether P1 runs first or P2 runs first, because all we care about is we try to calculate the total execution time for both processes. Okay, so we just want to make sure both processes complete the job, and then we check how much total operation times the computer system can actually use. So let's start with P1. So P1, based on the problem, P1 gonna execute for 10 time units of computer bound operation. So that means you're gonna use the computer CPU for 10 time unit. So once it's done, it's a time 10. Now once P1 finish the CPU operation, then you're gonna follow with the IO operation. So P1 gonna use IO1. Now during this time, the CPU gonna be idle, right? Because P1 just complete the CPU. But P2 cannot use the CPU because the operating system does not support multi-programming. So now P1 is using the IO1, so that means CPU cannot be used by any other program. So once the P1 is done at the time 20, now P2 is going to start to run on the CPU. Now P2 run for 10 time units, so from 20, then it will complete at the time 30. And then once P2 complete the CPU operation, you're going to be followed by the IO operation. In this case, it's IO2 for another 10 time units. So you're going to finish at 40. So what's the total operation time? 40, right? Now let's take a look at the second case. So if the operating system is supporting multi-programming, now what happens? So again, we assume that the P1 gonna start first. So P1 gonna take the CPU and then run for 10 time unit and complete the job at the 10. And then it's followed by the IO operation for P1. Now, during this time, the CPU is idle. So the operating system gonna say, well, because I'm supporting multi-programming, so I'm gonna actually load program 2 into the CPU. So in this case, both P1 and P2 are running concurrently, which is good, right? So now at the time 20, P1 complete job because P1 finished IO1 and P2 complete the CPU, operation. So then it will be followed by the IO operation for P2. So P2 gonna finish at the 30. Does it make sense? So the total operation time is going to be 30 time units. Now let's take a look at the time sharing. So time sharing, as we mentioned, that the time sharing, it is a multi-programming, but the switch of the programs is mandatory. So, which means if P1 is taking the CPU, now depend on how much time period each programs are allowed to use the CPU. Let's say the time interval is going to be 2 time units. So that means each program going to take the CPU for 2 time units. And then it will be removed. And another program going to be actually going to take the CPU. Also 2 time units. And then once the 2 time units is actually elapsed, and then it will be removed and the other program going to be loaded. So, but each program only allows to run for 2 time units. Okay. Now what's the total operation time with time sharing? Now, we assume that the time period for each program going to be 2 time units. Okay. Now, later we will find out it doesn't really matter what time intervals each program going to take. Now, let's take a look at this. So, suppose P1 start the CPU operation, and P1 runs for 2 time units, and P1 after 2 time units, P1 was kicked out, and P2 is loaded. Also for 2 time units, so P2 completed the 4, and then P1 is back for another 2 time units. That's 6. P2, P1 again, P2. Now, how many fractions do I need for each process? Because each time you're going to run 2 time units. So the total CPU operation is going to be 10 time units. So I need 5 pieces, right? Let's say 1, 2, 3, 4, 5. So you have 5 fractions for P1 and also 5 fractions for P2, right? So because each running total of 10 time units for the CPU, so the total going to be 20 after both actually complete the CPU. But the P1 actually finished a little bit earlier, 2 time units earlier than P2. So P1 finished over here, so P1 start to run the IO, right? And the P2 gonna run the IO 2 time units later. Okay. Now what's the total time? Total time is here, right? Because we have to make sure both process complete the job, the CPU operations or the IO operations. So P2 actually complete the job at the, so the IO operation is going to take 10 time units, starting from 20. So it's going to be 30. So it's 30, right? With the time sharing. Now you can check if each program are allowed to run for 1 time unit and switch to the other for another 1 time unit and switch back for 1 time unit. So instead of 2 time units, you will find out there's no difference. It's also the total operation time is going to be 30. Now this is based on the assumption that when I complete the P1, the program, and switch to P2, and there's the time interval between P1 and the P2 is 0, so that virtually the switch does not take any time. That's not true, right? But many times it's ignorable, so we just simply ignore this switch time. So sometimes we call these context switch time. That's the topic we can talk about later on. Okay, so here are the answers. Okay, for 3 cases, without multi-programming, with multi-programming, and with a multi-programming, in particularly with time sharing. So definitely the multi-programming is better than without multi-programming, right? Okay, to wrap up the section 1.1, so we actually gonna introduce 2 type of, processes. It's based on the process behavior. One type of process is called a compute bound process. So that means sometimes it's called a CPU bound. Okay. So that means this type of process can be used most of the CPU time, but they infrequently use the IO device. Now the other type of process is called IO bound. So that means it's basically use a little bit of CPU and mostly going to frequently use the IO device. So you're going to actually have a long CPU burst for the computer bound and infrequent IO wait. And also for the I/O bond, it's going to use the short CPU burst and a frequent I/O bond. Okay. Now these two different type of process going to actually make things slightly different. If you try to use multi-programming, you will find out you're going to benefit a lot for the I/O bond, but not much for the CPU bond. Think about this. Okay. If you have any question, just ask me. Thank you.